I certainly did not realize there was a connection between these various proofs in different branches of mathematics.
Right, this framework is quite general, I would say. Right. Actually, there is another paper trying to generalize, which is trying to generalize this result. That's was the paper which I was actually interested about learning about it. There is an application of this lower fixed point theorem in Y combinators. So Y combinators is a special case in lambda calculus. Have you heard about Y combinators?
Yes.
Okay. And there is an interpretation of there is a relationship. I don't remember it exactly, but there is a relationship between Cartesian closed categories and lambda semantics of lambda calculus, or kind of semantics that could be assigned to lambda calculus. And the generalization of this framework beyond Cartesian closed categories, it is the author from this paper was asking himself about the semantic for something called magmoidal categories. I'm not sure that I understand it very well, but
Right.
Sorry, did you say monoidal categories?
right, magmoidal categories is right. But actually, I don't understand this paper. It's quite complicated. It is it seems quite complicated for me. You know, I don't know enough category theory or
we looked at
understanding it.
monoidal categories for one thing, I guess, when we were doing Bartovsky's thing about a monad is just a monoid in the category of endofunctors. But yeah, you get into those categories and they sort of generalize Cartesian ones. So.
Right, but you are talking about monoidal categories.
Yeah, I thought that's what you were talking
about. No, sorry about my pronunciation. I was saying magmoidal, not monoidal. Magmoidal.
Oh, okay.
Right.
It's like somebody's name. Where is it?
Well, I think we should start with the current paper and see what questions people might have on it.
Yes.
Right. I am looking for something, but you can just continue with your discussion.
Right. So, I mean, I guess my first question is, I don't understand the notion of proof theoretic strength, although I know it has something to do with comparing the sizes of different infinities, basically. Is there a connection in this paper? I mean, the first instance of this pattern, which is Cantor's theorem, is obviously it's comparing Aleph null and Aleph one. And then the other examples have to do with sort of self-reference or things that can't be proven in the system, and there are limitations on I guess the proof theoretic strength of the system. Is that a coherent thought?
Right. I didn't thought about proof theoretic strength reading this paper, but it makes sense for me. But
So what is
I
proof
hear
theoretics? Go ahead. I'm sorry.
right. And the same question. I have no clear in mind what is proof theoretic strength actually. I have a vague idea, but it would be you know I don't understand it in rigorously.
Right. I don't understand it. Well, I probably understand it less than you understand it. But when I've seen people talking about proof theoretic strength, they always go into something where they're comparing the size of different ordinals or something. And so I'm thinking, well, okay, so it has something to do with comparing the sizes of things, but I still don't understand exactly what it's about.
Right.
Well, he mentions one of the incompleteness theorems of Gödel, right?
Mhm.
Right.
I
Right.
don't remember all of them, but it has the form of, you have a formal logic, and you construct a sentence which is clearly we can see is true, but which exists in that logic, but cannot be proved within that logic. Does that ring a bell?
Right.
Mhm.
I think that's a pretty good summary.
Yeah, certainly seems to be in the same neighborhood.
Yeah. So
Yeah, it seems like
that,
this
I guess,
paper is a lot. Go ahead. Sorry.
I guess that relates to proof theoretic strength, but I don't think it particularly has to do with like the cardinality of infinite sets or anything like that, as far as I know.
Right. But every time I see a discussion of proof theoretic strength, it starts talking about the cardinality of infinite sets. And so, I mean, I've never seen an actual definition of proof theoretic strength. So I don't get the connection, except that I think that there are people who think that there's a connection. So
It seems to me that this paper is really more about the sort of self-referential situations where you have a logic and like what Hugh said, you can basically show that within that logic you can't prove everything. And so proof theoretic strength to me roughly sounds like you've got one theory, you've got another theory, and the other theory can prove more things than the first theory or something. But I don't think he's so much comparing theories. It's more like you have a candidate theory, and then within that, you can show that there's a potential paradox.
right.
But you can get out of it by basically saying that you have to you have to structure things in a certain way. That part I don't really get, though.
Right. I mean, your logic is constrained in a way that such that a naive definition of the syntax doesn't express all of the things that are not allowed. So you can make an apparently syntactically correct sentence that is self-referential that isn't allowed, and so you have to express the constraints on your logic in some way other than just saying, here's the syntax, and anything in this syntax is allowed.
Allowed as in provable, or
Right. Well, yes.
depending on it. Yeah. Okay.
Or even, I
Well,
think that's particularly true when you get into natural language, because there are examples in here which are more like puzzles than theorems, where you talk
Yeah.
about the things that you can express in English, and that it's not too surprising that paradoxes arise from there. Like Grelling's. Anyway, somebody should show us the text. I can do that if no one else wants to.
Right. Before that, maybe someone, maybe Peter, which is a common presenter, could share this, because maybe we could clarify a little bit about proof theoretic strength from this side, and looking at a couple of paragraphs. So
Hugh, do you want to do it, or should I do it?
right. If it will be great if it will be great if you can share the link I have shared in the chat.
Oh,
If we could take a look at it.
is it the web page itself, or
Oh.
is there something I need to download?
No, it's just a web page.
Notes on proof theoretic strength.
I was
Uh,
you know.
Let me drag it over here. Okay, now go back to this. Oh, somebody else is sharing. Okay.
I attempted to share. Did it work? Do you see a large blue screen with text on it?
No,
No.
No. What do you
I
see?
see something that says double click to enter full screen.
I see
Oh,
something that says Hugh Wolf has started screen sharing.
oh, here. Let me, and then maybe I paused. It's paused. Why is it paused? Maybe I need to log
Click
in.
on.
All right, I'm gonna quit. But maybe I'll try again.
I think I can share it.
Yeah, give it a go.
Is this, well, I
Ah.
just did, sorry.
Okay, now
There it is.
Is that the one you're talking about, Antonio?
Right. So, right. We have an introduction, but the two interesting things I see is the couple of paragraphs, below of Bison, talking about reducibility and ordinal strength.
Maybe we should come back to this. Unless is there something you want to point out specifically?
Right. Well, the introduction section there is sort of hand wavy, but it does say the last paragraph talking about the different ways in which proof theoretic strength can be measured.
Right.
Ordinal strength.
Right. One important concept is reducibility. If we could reduce one theory to another and vice versa, these two are equivalent. Or if we could reduce just one of them to the other, then the other is stronger, I would say. And the other concept is the ordinal related to a theory. So it is say here that proof theories say that alpha is the ordinal of a theory T, provided that alpha is the supremum of the probable well orderings of T, in the sense that for some natural primitive recursive well ordering of type alpha, T proof I for every initial segment. So I cannot parse this paragraph, but I think that here there is the definition of the ordinal related to a.
Right.
I don't know if maybe you could help with initial segment of Q. What is I of Q? Do you know?
I don't know.
Maybe I of Q is the set of initial segments of Q.
I think we
Well,
might
no.
have to study the Beeson text in order to figure that out.
Yeah, that's one way to do it.
Oh, I is defined here, I guess.
Oh,
I guess, except I don't, yeah. Except that has two parameters. Oh, well. Oh, and then he proposes just a single line with a single parameter. It's abbreviation for that. So, but yeah, I don't want to try and figure this out on the fly, I think.
yes, this seems like something that could require a fair amount of study before being able to interpret. But it does seem like there's some connection here between the limits on what you can prove and the size of numbers. And then this paper starts out by showing that one infinite number is smaller than another infinite number, and then goes on to talk about some paradoxes, which are the limits of things that can be proved in various systems. And so so it just seems like the topics here are related to proof theoretic strength in ways that I might understand if I understood proof theoretic strength.
Sorry, I'm back because the connection is right. Right. I believe.
I guess you're gone again.
Looks like.
Yeah, should we go on to the paper
The
or?
paper itself, yeah, that probably makes sense. Since none of us can actually explain what proof theoretic strength is, I guess this is a dead end for now.
I think it's pretty the same as provability, nothing more.
Yes, but why is there this connection between the sizes of ordinals and provability? I don't quite understand it.
No, me too, either not.
Do we have questions about things, or how do we want to proceed? I mean,
I have a comment, but it's rather going astray, so I would wait for the end with it.
okay. Yeah. I think sort of the key thing is like that if you have these systems, you know, where you have a set T, and then something like the set Y, which is the properties, right? Am I getting it backwards? Yeah, now Y is the properties of T. Then there can't be a function from T to Y functions that captures all the functions in, you know, all the T to Y functions.
Right.
I think that's what it's saying.
Right.
Because you can always construct one that can't be one of the functions that f hat would have generated, because you can diagonalize across everything and make sure that it's different from every other function.
Right. As long as y is non-trivial. That is
Right.
to say.
Right.
Yeah.
Yeah, and this part was new to me actually. That you can phrase it as you know, the fact that one can't represent all things that way, or you can phrase it as, if you can represent, if all of those things are representable, then y has, let's see, what y is trivial in the sense that any automorphism of it has a fixed point.
Yes.
That contrapositive form.
So I wasn't sure why fixed points were bad.
Well, think of t as the naturals and think of y as digits. So what we're saying, what Cantor's theorem is saying, is that the set of naturals is smaller than the set of reals. And so you're representing a real as a function from a natural to the digits of a real. And so if you are representing your numbers in base 0 or base 1, then nothing works. Basically, you have to represent your real numbers at least as a string of digits in base 2 in order for the representation of a real to actually be to correspond to our notion of a real. And so
But then where does the
2 is the smallest set where you have a function from 2 to 2 that doesn't have a fixed point.
Right. So we could not represent a real, or try to represent a real from an array code. That's a natural.
So in this
anyway,
case, t is real, right? And y is 2.
Right. Well, y could be any number greater than 2. You can think of it as the base of the that is used in the string of real digits.
right.
But then again,
Not a
I'm
thing.
still not sure why the fixed point matters, right? If you have a
Well, in Cantor's argument, the original one, you look at this diagonal, right? And then you say, I'm gonna use this diagonal to produce a number which is not on the list. And to do that, you look at every digit on the diagonal and you change it, right? You maybe flip it from between 0 and 1, or if it's decimal, maybe you you know, whatever, you increment it by 1 and looping back around to 0. But you have to be able to change it in any case, right? So if your set of digits is so small that you can't actually change it reliably, there is no sort of changing function, then you're stuck. And the original
or
Cantor's
if your set's big enough, but you just pick a function that has a fixed point, then at that point you won't be able to flip it. So I guess that's the point. Yeah. The fixed point means that there's at some point where you can't flip the digit, you have to leave it the same. And that breaks the argument.
Right.
Yes.
But yeah, okay.
Although, as the author points out, when he gets onto other examples, which are more about sort of the strength of proof systems, the examples of y in his square diagram don't really feel like truth values particularly. So he raises the question, are these truth values in some sense that, you know, we haven't yet articulated? I think he gets into that way at the end, but there is a bit of a jump there.
Hmm.
Mhm.
Something that something that came to my mind reading this part was clarification in Haskell. I don't know if you thought about the same thing, but I was asking myself, does it mean that not every function can be clarified?
Could be what?
Can be what?
Clarified. Do you know what
Oh,
clarification?
Curry.
Clarification in Haskell, something that is right. So it is related with clarification somehow. It could be the case that not every function could be clarified.
Yeah, now you're getting into constructible versus non-constructible functions, right? And the diagonal argument assumes that all functions from T to 2 exist in a set theoretic way. But in Haskell, you cannot define all functions from T to 2. You can only define the constructible by definition, right? And you can enumerate all constructible functions. So there is no paradox there.
Okay.
I think in this paper, computable function is what is equivalent to what you were just saying
Yes.
as a
Right. Yeah.
But
And
also, there's a, sorry, go ahead.
I mean, later on, he mentions Scott domains, but there is a way to represent like 0, 1, you add a bottom element that is less than true or false. And then all functions, there is a fixed point, right? The bottom is a fixed point. But anyways, yeah, go on.
Oh yeah, I was just going to say so near the bottom of this page, he says, rather than looking at functions from t to the y, or y to the t, whatever, we look at equivalent functions, right, from t cross t to y. That's currying right there.
Yeah.
Right.
And that does seem to be an important part of this. And I seem to remember earlier on that the category theoretic version of this, which Lawvier published many years ago, was in the realm of like Cartesian categories, Cartesian closed categories,
Yeah.
which you would need, right? If you wanted to do some currying thing like this, you would need exactly that Cartesian
Yes.
Right.
property.
Which brings up a connection to the paper for our other track, which we will be looking at in 9 days. That's actually about Cartesian closed categories and some clever stuff that you can do with them in Haskell. So that's kind of interesting. One thing that kind of bugs me here is that a Haskell programmer would put the arguments to F in a different order so that the partial application of F can be written as a concise expression without using flip. But that is to say, you would say—
Because the T prime ends up being sort of, the second argument is the one that's fixed. And then you
Yes.
have to do F
Yes.
dash T prime, right?
And the Haskell
Yeah.
programmers are very careful about choosing with the order of their arguments, because they want the one that is most likely to be fixed to be the first one, so that you can write your function as partially applied.
Right. Well, I wonder if, in the category theoretic sense, functions from T to Y of T are different than exponentials. The Y to T sort of looks like an exponential, and I guess, they're exponential objects, and then there's ways that you can kind of curry them by using various operators. But maybe he does it sort of in that order because it's sort of the exponential thing is the target thing. And you're sort of saying that you can't have an f prime from t to y to the t in those situations. That covers all of the entire exponential. It's not onto. You can't have an f hat that's onto.
Right, but I mean, notice that he's switching the order between f and f hat, switching the order of the parameters.
Mm-hmm.
That's something that a Haskell programmer wouldn't do.
I see what you're saying. Since he has the choice of picking t. Yeah.
I assume he has the choice, but maybe there is some historical reason why he has to connect it.
Right.
Connect it to previous literature by doing it in the opposite order.
I don't think there's any difference though, right? I think the proofs are exactly the same if you use f of t prime comma dash.
They should be, I assume
Yeah,
so.
I think they're identical. Yeah, I don't think that makes any difference there.
Right. This is just this is something that seemed minor, like a minor irritation to me, rather than anything of theoretical import.
Okay. Yeah.
But if you were doing these proofs in Ogda, you would definitely choose the opposite order of parameters for f.
Right.
Well, I have a broad question about, well, I have a question about things somewhat later in the paper, but I wonder if anyone has a question from the first several pages, perhaps. That we could.
Yeah, I had a problem with like this last statement. If this system does deal with G, there'll be an inconsistency, again, a fixed point. And yeah, I don't know. I guess maybe we answered that, but I don't really see why a fixed point results in an inconsistency. Is that because that's the case where you can come up with a paradoxical thing? Right.
I
It does
think-
deal with G.
I think that's because if you interpret the set 2, 0 and 1 as false and true, then a fixed point mapping 0, true and false to itself would be something that's neither true nor false, right? And so if you only allow set theoretic functions from true
No, a
and
fixed point
false,
would be true to true. Right.
but it'll also map, you could also map false to false, right?
Mm-hmm.
I mean, but in a sense, you're mapping.
I think that in the examples where a fixed point is viewed as an inconsistency, the set y is no longer just 0, is no longer 2. It's now something quite a bit larger.
Right, but it applies to 2 as well. I guess that's the thing. So what is why is fixed point leading to inconsistency is the question, right? The existence of
I think in a lot of cases Y is sort of 2, but go ahead.
Yeah.
So what do you think he means by inconsistency, other than fixed point?
Right.
Well,
not...
is that inconsistency equivalent to existence of paradox or something?
Right. Something is both true and something is false, like the Russell's paradox. And the reason why since it can be both true and false, under the assumption that there is a fixed point, you cannot resolve it because it flips back and forth. So I think I think the relationship with the lattice theoretic approach, which is what Scott domain is, I think makes it more interesting because the notion of fixed point is a key property of continuous functions in that domain. Whereas in set, you have these issues. So there are, different ways of resolving this. And one is that, if you limit yourself to continuous functions from t to y, under a suitable definition of continuous, then there is an onto. And that's what, the infinity construction by Scott shows. And that's why lambda calculus is not inconsistent. Whereas in set theory, it is inconsistent because you cannot have a object that's both a function and an object itself. So, but that's getting further afield here.
Maybe you should do a tutorial on that.
Right.
Anyway.
Yeah, because they mention later on that, that in set we have issues, but in other categories, there are structured functions, right? There are functions that
But the
have
sets have structure and the
Right.
morphisms have to.
Right. So for example, if T and Y are groups, then they can only be group homomorphisms, not just arbitrary set functions from one set to another, but from a group to a group. Then there are restrictions, and then this Cantor's theorem may not apply. I guess that's the thing. And that's, well, this is my bias again. I think that theory is is a huge rabbit hole that modern mathematics has created that causes all these antinomy contradictions. Whereas if you stay in a constructible universe and you limit yourself to things like that, then these these paradoxes basically disappear. But
I agree.
Anyway, the concrete example about the first incompleteness theorem of Gödel, talking about how a fixed point may result into an inconsistency, is shown in the page number 16 as first application. So, and it is pretty short. So maybe we could understand,
Okay.
right.
Does it start here? Or, okay.
No, below. The scroll up
Sure.
a little bit. Right. This one, this first application.
Right.
Right. So
actually, before we get into that, I have one question about notation that maybe people can answer. The square bracket notation, the left and the right, angle square bracket on an expression.
Mm-hmm.
What is the meaning if there is a free variable x? Is that x part of the object language that is being quoted? Or is that x a free variable, which means that it's a function from an expression into a encoding? Do you see what I'm asking?
I think so. I think g of x is an expression that has x as a free variable, but we're gonna use x. We're gonna feed, so this whole expression is a function of x, right? And so we're gonna feed different things in as x possibly. And
I got the opposite impression actually, and I'm not positive about this, but I feel like when they say script g of x, let's see. Oh no, you're right.
I mean, look, just even this expression, right? This is an expression that we're feeding to, or this is a different expression that we're feeding to the bracket constructors.
Yeah, you're right. So
so
g is an actual function which gets applied to things. Yeah. But
Right, and X is
sometimes,
the
like
variable.
earlier on in this paragraph, I think like upward says script B and let's see. Can we scroll up a little bit? Sorry, can we look
Sure.
at this? Yeah, okay. So well-formed formulas with a free variable. So script B of X and script H of Y. In those things, so we're not actually evaluating script B on X here. We're saying that script B is a formula in which X occurs in a certain way. Is that right?
Right. I think so.
Okay.
Yeah.
Okay.
So that threw me.
And then
for a
when you
little
do the brackets over that, you're sort of taking the Gödel number of that, but it depends on X.
No, X is now fixed, right? X is now just a symbol
I think so.
that you're taking the Gödel number over. Okay.
I think so in that case. But farther down with the other example, I'm no longer sure.
Yeah.
But
But when you have nested, like on page 16, if you go down just a little bit, you see the issue I have is when you have the nesting. So what on the right hand side of the by definition, so we first take the Gödel number of Bx, and then we stick that Gödel number where the X occurs in the expression B,
right.
and then we're now taking the Gödel number of that. So is
Right.
that correct interpretation then? Okay,
That's my interpretation.
I see. Okay. Yeah, I
And I think
find this notation a little bit tricky because it's kind of like quasi quoting where sometimes it's the fixed and sometimes it's not. So, right? So the angle bracket is not a part of the object language. And therefore the angle bracket B, the outermost angle bracket, fixes everything except for if it sees an angle bracket, then we do a substitution, right? So, oh well, okay.
yeah.
I guess it's part of our definition of formulas that one can always substitute things into them, which I think is the SMN theorem that I looked that up, and that has basically to do with substituting explicit values into some formula or program that you already have.
Okay, sorry for the digression here. Okay, so what, Antonio?
Right. A little bit below that. The as first application about that, it is shown that a little bit down
Oh,
here.
yeah.
Right. So then this epsilon x construct this way. That's the with that constructed this way. What would be what is a fixed point for this epsilon x? It is saying that it is a sentence that it's equivalent to its own statement of probability. But it is not about inconsistency, but just about incompleteness. So, right.
Right. It does seem right.
So, have you read that fixed point leads to inconsistency result, or I feel confused about that.
Maybe should we back up a little bit and kind of maybe go through things, because it kind of builds up to this. I don't know.
Right. I don't remember about inconsistency result. related to fixed point. Paradox.
Yeah, I don't know what
I
consistent and mega consistent theories are. So
right. I will say
lost
that
there.
I will say that what leads to an inconsistency is assuming that we can express or we can prove everything from inside a theory. In the case that we don't have a fixed point. So the way to the inconsistency or to the paradox is without having fixed point, we cannot define the value of true of any statement of a theory from inside this theory. And assuming that we can do that, then we get a kind of any kind of inconsistency. And having fixed point leads to incomplete. It is related to incompleteness, but not to inconsistency. It makes sense.
I think so, yeah. And I think given the way all these other ones work, I think he's saying that you can come up with a fixed point for this E of X, or whatever, script E of X, using the kinds of constructions he's been using up till now. And so that's where you get the incompleteness, the theorem, incompleteness there. Because that would be one way to do it. You basically use this diagonalization argument to come up with your G, which then is the fixed point, which then, if you didn't have a fixed point, would be a contradiction. So,
right.
Yeah, it's that G is it the fixed point of E? I'm not sure now, but
If we actually the function for which we look for the fixed point is E.
Okay.
Actually, I have a notation. I have a notation question about the previous page as well. Could we go up a little bit to the statement of the? Yeah, that's fine. So theorem 4 at the bottom, diagonalization lemma. That turnstile, that little sideways T there, in the central formula. I'm reading that as something like, we have a proof that the following thing is true.
Right.
Is that right?
Yes. That the following statement is provable in the logical framework that we are dealing with.
Okay, and it's different. If we deleted that turnstile, then we would just be quoting a formula, and so it's. I'm trying to figure out a semantic function of that turnstile. We can't just say that C is equivalent to E of blah, blah, blah. We want to say that it's provable within the system, and that's why we put the turnstile in. Is that right?
Yes, it's asserting that.
Cool.
And the double arrow in between the C and the E, usually that's written using a double layered arrow, right? If and only if. In logic, you have a left arrow and then you have kind of like an equal sign and then a right arrow. Whereas here, it kind of looks like a function from one to the other. But it's saying C if and only if epsilon of quote C is provable.
Cool, thank you.
I think it ends up being a function, right? Because if you have a proof of a closed formula C, then you can get a proof of this and vice versa, right?
Yes. Yes.
But you can do it in a provable way, which I guess means that then you can count them.
Yeah. So the slightly above that theorem 4, the definition of D is interesting, right? That there.
Oh,
That
in here.
yeah, we shall assume that we are working in a theory where there is a recursive D from naturals to natural that is defined such that the encoding of a formula B of X is the same. I mean, we can then compute the encoding of B of X on B of X. So I'm wondering why that is significant here.
Yeah, and why would we even believe that it's plausible?
Yes.
Right. I don't understand.
Yeah, I mean, yeah, I always get thrown by them having the B of X, or
I mean,
in sort of the left-hand side of the equation. I think there's an isomorphism here, and you're reversing it. So you're basically saying if you have a number, then you can turn it around and get the B of X formula that corresponds to it, or something like that.
yes, I think that's the implicit assumption, right? Given any number, we can get the Gödel number, I mean, the expression that it's the Gödel number of.
Right.
But it may not be defined for all integers, right? Not all integers have that. But if it's something is a Gödel number, then we can get the formula out of it. Then we can create the Gödel number of the Gödel number and insert it into that formula. So, okay, I guess I believe that.
Why did you say that not all numbers, not all Gödel numbers correspond to?
No. All integers are not necessarily a Gödel number of some expression. So D is not a
You
total
mean
function.
that, right? First of all, yeah.
Yes. So D
Yeah,
is not total, right? Because the number
yeah, I think
one,
it is.
you think it is. So what is the Gödel
I think that's what recursive
formula?
means.
Then what is the
It's not
Gödel
partial recursive.
expression for the number 0 or the number 1?
Well,
I think you're talking about something different. So D is a total function, and it is recursive. That seems clear. But I do think that for this, Young-Il is right, and we don't have to assume that Gödel numbering is onto.
Okay,
right?
so we're only applying D to Gödel numbers. Okay, fine. That's the same thing.
Yeah, we don't care. The requirements on D only relate to values that are actual Gödel numbers, right? D can do anything on values which are not Gödel numbers, and it will still satisfy.
Okay, sure.
Okay, but I know
my
okay.
I mean, my understanding of Gödel numbering and those sorts of things is like, right, you have a language and it has this, a set of strings in it, and you basically enumerate them, starting with like the empty string, and that's 0, and then 1 is maybe X or something, I don't know, but basically every number corresponds to some formula to some sentence in that language, right? And those sentences are all formulas. So every Gödel number corresponds to some sentence, it might not compute anything.
I
It might
see.
diverge or something, but
Okay.
every number corresponds to a thing, and everything has a number. You can go back and forth.
I see. So basically, you're enumerating all well-formed formulas, right?
Yeah.
And then you're associating that formula with the number that, I mean, if it's the nth formula, then that's what n it maps to. Okay, I see.
I think so.
Okay, I was thinking of more kind of recursive definition, but I think yours is fine. Yeah.
I think it's true that the original Gödel numbering was very far from being onto. I think you took prime powers and then multiply them together.
Oh,
But it's possible to imagine that you could make it onto, and that would be okay. And in fact, farther down in this paper, there's something called Lob's paradox, LOB, where, as a counterpart to the upper angle bracket thing, there's actually a lower angle bracket notation, which is the inverse.
Yes, the inverse.
That takes
Uh,
the
yeah.
Gödel
I-
number and
we
sort
have
of-
this lower bracket of upper bracket, so like kind of funny. It's the
Yeah.
yes.
And I think that this would go the other way too. If you had n and took the lower bracket of it and then did the upper bracket, you'd get n back.
But yeah, I think they're supposed to be inverses. So one could
Ah,
imagine that there's I mean, certainly you want the formulas to be only countably infinite, right? So there is some enumeration, whether or not it's like computable in a practical sense, I don't know. But yeah. Anyway, so there's that too.
ah,
I mean, I come at it more from, computer science, and in grad school, we did a lot of diagonalizations of Turing machines and things like that. And the whole key is that you can sort of enumerate your Turing machines and kind of come up with a number for the Turing machine that looks like an input to a Turing machine. So the fact
right.
that you can enumerate them is important.
Right. The existence of
I
a
don't
universal
remember if
Turing
it
machine.
has to be onto, but anyway, sorry.
Yeah. The proof that there is a universal Turing machine that can simulate any other Turing machine given a number, right? So, yeah.
Right.
But have we understood then the application for Gödel's first incompleteness theorem then?
Where's that? That was back up here, right? 16
Yeah.
or something.
Because here, the existence of a fixed point for E does not imply inconsistency, but actually shows that it's an incomplete system. And I think what's
Right.
interesting here is that if you assume we are in a consistent and omega consistent theory, and that's a huge assumption, right? Then E of X has it has a fixed point, then it's asserting that I am not provable, okay? And that is, I have a hard time getting my brain around this one, okay? That we can prove that there is a statement that is true that says, I am not provable.
Right. But I mean, I think, this is, has something to do with it, right? You're basically saying, that for all Y, you can't prove X, right?
Right, right.
So
That there is some X for which that is true. Now, finding such an X, of
But
course,
why
is a completely different issue, right? We can show that it
Right.
exists, or does it exist? Okay,
I
does it
yeah.
always
I
exist?
mean, I
or is
think
it
if we go back, where was the first thing of Gödel? Oh, that's Cantor. No. Right, he does Gödel twice, right? Or is it Cantor he does twice?
I believe that it is Cantor what is done.
Okay. Russell's paradox. Another paradox, liar. Okay. Shoot. But anyway, I mean, all through here, he ends up, coming up with this G by diagonalizing using the function that presumably, maps numbers into formulas or whatever. And then he has the alpha that flips things. And by coming up with that G, you can come up with, something where it's not equal. And now in the section we're in, I think he's flipped it around to the contrapositive. And so when we get down, where to go? De Gödel's theorem, I think it's still, you can use the constructions above to come up with such a G that would be the fixed point of E. That makes sense?
Where is this prove defined? This PROV?
in that
I think
in the
he's
sentence above?
Oh,
Yeah.
sorry.
Let prove yx stand for the encoding of the proof y. Y is the encoding of a proof of the statement that is encoded by X.
Okay, so Y is the witness that X is provable,
Yes,
roughly.
yes.
Okay, thank you.
I mean, does it even make sense just that prove y of X? I mean, you can write any expression down, but why is the Gödel number of a proof of a statement whose Gödel number is X mean?
I think the idea is right. You can enumerate the sentences, but you can also enumerate the proofs, right? So Y is the Gödel number of some proof, X is the Gödel number of some statement, and checking that is straightforward. It's, you can check that the proof is a proof of the statement, right? I think that doesn't take anything special. So I think that proof of yx is just, that's an okay function. But then but that itself has a Gödel number. And if you put for all y not of that in front of it, it also has a Gödel number. And I guess that's where things break down. But I'm not sure. I keep looking at what the fixed point of this E of X. I mean, what does that mean, that there's some number like Z such that Z equals E of Z?
Well, the fixed point of E of X is asserting that the sentence itself, right, the whole thing, that I am not provable, the outside sentence is saying, you know, for any integer, there is no proof of X, right?
I would question that. I think it can't be.
Right, right. But the meaning of E of X is saying that I am the Gödel number of the assertion that there is no proof of me, right? This is the self-referential part of it. So the X here stands for the whole thing outside. That's the fixed point.
Wait. Oh. Say that again.
But it's itself an invalid sentence.
Maybe, but that's what Gödel's incompleteness is based on, is that there is a sentence for all y not provable y. Okay, if we replaced okay, the right-hand side by itself makes sense, as Pete said, right? We can assert that there is a provability relation between two Gödel numbers, and we can assert the negation, and then we can assert that for all y, we cannot prove X.
Well, for all y is not a proof of X, roughly speaking.
Correct. Yes.
Right.
That means like, well, so basically it says there is no proof of
X.
statement X. Yeah.
Right.
Right. And
So
so,
now
then
what-
is this the Gödel number of that? Oh, go ahead. You were
Script E is supposed to be a well-formed formula with one free variable X.
right.
Right.
And I guess in our theory, we assume that, you know, our language is powerful enough to say that thing that we just did on the right hand, right? That we have universal quantifiers and negation and all those things. And
right.
so it actually really does look like a well-formed formula with one free variable X. So I believe that.
Okay. So this is the definition of E right here. Okay.
Yes.
Yeah.
Right. But I see what you're getting at, Pete. What does it mean to be a fixed point of E then? It's a formula, right? Or is it a number?
I was thinking about that. I feel that it is a formula, not the coding of the formula, but just the formula.
But it's
No,
not.
But if they're
not E itself
isomorphic,
that
it
has-
doesn't matter.
It's not
X
E
has-
itself that has a fixed point. It's phi sub E.
So X has to be a number here, right?
Yes.
Yeah.
So E is a formula over X, but X has to be ranging over numbers.
Right.
Okay,
Gödel numbers. Yeah.
right. So a fixed point means, yeah, what does it mean? What does it
it's
mean
not-
to be a fixed
it's
point
not-
then?
It's not E itself that has the fixed point, right? It's the right-hand arrow of the square, which is phi sub E.
But if you
shouldn't-
look at the beginning of the chain of equalities, so this E of G, but okay, great, but it is okay. So E of square of G up square of GX, it is the same of this phi sub E. So it seems that the definition of phi sub E, it relates with E through these up squares. So X should be a number, right?
Mhm.
But that doesn't is not consistent with the theorem 4, where it says that X is a free variable. Yeah, a little bit more, a few more lines. Yeah, you see, in the right below the theorem 4, the numeral 4, with X as its only free variable. So E is mapping a free variable to a formula. So what does it mean to be a fixed point of E?
Well, if
I'm
you
now
Right.
really confused.
Right, but
you
they're not
instantiate
saying
the free variable with something,
But then
then
here we're now going over
Here's, by the way, here's like the fixed
numbers.
point of E up for this thing, right?
but
You were
not quite
showing that,
because there's the square brackets in there as well, right?
Yeah.
If we're
I,
evaluating
I,
E on a square bracketed expression, and we're getting
oh,
what's inside the square brackets as the result. So there's an
right.
extra,
Actually, it is not a fixed point of E rigorously.
the fixed point of phi
yeah,
sub E. And phi is defined up at the top of this page, right? Phi takes a formula
Ah, okay.
E evaluated on the Gödel number of that formula.
Okay.
Aha.
It takes a formula to a formula.
right. So it's the fixed point of this. I guess it actually does say that, but at least here, yeah. And then this is the fixed point, I guess they're saying.
Okay.
This guy would
So,
be the fixed point of that.
okay. So in the sentence we were reading before, it should be a fixed point for the phi sub E related to this E of X, right?
Yeah,
Not,
I think so.
it's right,
Okay. Okay. That makes more sense.
That does make more sense.
right.
Yeah. I think they
So
could have done a
having,
little bit better explication here.
right. But, defining the E of X, we have the phi sub E already defined from, above. So I believe that, that's right. It should be more, you know, I trying to not being redundant. It is,
Yeah,
confusing.
yeah. He's kind of, speaking a little bit informally here, and people that completely understand the stuff will go, oh, well, he means that, not what he's actually saying. But to us first time readers, who it's like confusing.
Mm.
I'm confused again. The second line of page 16 at the top is, or the first line at the end, P is mapped to phi sub E of P, which is equal to E of encoding of P. So now E takes an encoding as the parameter. So maybe
Mhm.
they do mean X on the bottom there of the, yeah, E of X, maybe X is a numeral or a number.
Right. Right. Was Gödel
But it
numbers
is a
is
Gödel
X,
number.
right?
But
It's
then is the Gödel number of is equal to this expression on the right. But then what is the X on the right side? Is that a Gödel number or is that a free variable?
No, this is a definition of E for, over NAT. E is like
Over
a
nat or
NAT
over variable?
formula.
Okay, over nat. So for each
Yeah, E
natural
takes a
number,
NAT to a formula.
we take it
And
to a
so
formula.
this is defining it, saying X is the variable. And so for any particular, like E of 6 would be for all Y not prove Y6. Right?
But I think the way that they phrase it in the paper is that E is a formula with a free variable. It's, you can view it as a function also, because substituting any particular number in for X will also give you a well-formed formula. But E itself, I think, fundamentally is not a function, but a formula that just has a free variable X in it.
Okay, so then a fixed
Any-
point is
Okay.
an infinitary formula, for example, like in the then let so what does a fixed point of E of X look like then?
But it's the E of X doesn't have fixed points. It's phi sub E that has fixed point. So if you look at the square there, right? The square phi sub E is mapping closed formulas, that is formulas with no free variables,
Yeah.
into itself, right? So for any such mapping of a set into itself, you can ask whether it has a fixed point. That's a sensible question. And how do you define phi sub E? Well, it's at the top of that page. You take no, sorry,
Where'd it go? Oh, here. Yeah.
that one. Okay,
Oh,
but if we
wait.
scroll
You're,
down to that top of the page, so the
Yeah.
top of page 16 there
First. Mhm.
defines phi sub E by saying, okay, if you're given a closed formula, how do you get another closed formula out? And the answer is you take the Gödel number of the first closed formula, you substitute it into E, and now E is no longer has a free variable in it. It's closed because you substituted a value in for X. So now you have another closed formula. So that's what defines the phi sub E. That's the down arrow on the right side of the square. Does that make sense?
yeah. So Lind1 is a formula that has one free variable.
Yeah.
And we copy it. And then we apply F to it, and that gives us back a closed formula. Because where's F?
Yeah.
We define F here, basically given two formulas.
Yeah, we encode the first and then we stick it into the free variable location. Okay.
The Gödel number of, yeah. We encode the first, stick it into H, right? And then we apply this guy to that to get a formula that has a closed formula that has the Gödel number of the thing we stuck in there within it.
Mm-hmm. Mm-hmm.
So we're going from a formula with one variable to something with 0, I guess.
Mm-hmm.
Oh, really?
Honestly, I still can't really digest the incompleteness theorem statement that we get out of all this.
Yeah.
A sentence equivalent to its own unprovability. And that part, I don't understand how we get there. I think it's trivial, but I'm not grasping it somehow.
Yeah.
Yeah, I'm thinking that, just looking at this, it's sort of like if you take this formula and put that into E, or put that into phi of E, I guess. Right. Right. E is some formula, has a free variable, which is a Gödel number. So this is a Gödel number. I think this is kind of maybe a little bit backwards or something. Because it's really this thing that we want the fixed point of. Right. But I think it ends up that this thing
I will,
is the fixed point of this modulo, you know, these an extra set of angle brackets, which is what E gives us. Yeah.
I have a question about that, because X, right, it is not a fixed point about E of X, but about phi sub E, phi sub E, right? So, right, so phi sub E is wrapping, so, but E of X, I am lost. I am lost again. So E of X, E is wrapping up a golden number, right? Because X is a number. So P sub E equals E of the golden number of P. Right. Okay, so phi sub E should wrap not X, but the expression, but the expression from which the X is the you know, the code, the golden number, the codification, right?
I think you're trying to say they should remove the upper square bracket
Right.
on the right hand side of the first line.
I mean that the fixed point, or the fixed
Yes,
point,
you're right. It's a typo.
Yeah.
right?
The phi E, the outer quote on the argument is incorrect.
Yeah, that's true.
Right.
Because the definition at the top introduces an quote when you go from phi to E, right? So there has to be one less on the phi E.
Yeah.
Then
E
the last
doesn't
line.
operate
That's
on
why
numbers.
this is the fixed point
Yes.
of
Those
phi
two
sub E.
those two shoulders, outermost ones, are incorrect. Yeah, good point.
I think
Yeah.
Janowski should have got a couple of friends to go over this maybe before he.
Yeah, especially in logic, notation is so critical here, you know? Regular math, you can get away with a little sloppiness, but okay. Sure, we agree that G, angle bracket G, is a fixed point of phi sub E, I think.
Right.
Yeah.
Okay.
And the fixed point of phi sub E is an expression, not a Gödel number.
Yeah, it's a formula.
Yes.
E sub B takes formulas as it acts on formulas,
Right.
not on.
So by definition of fixed point, and so the output is equal to the input. So
Yes.
right. So E of X should be a formula also. So okay, so the fixed point of, so we are looking for P for which the Gödel number is X, and the formula P is this formula defining X, defining E of X. This you know, this logic, this proposition. And the proposition says, right, the proposition says that for all Gödel numbers, we don't have a corresponding Gödel number for all Gödel numbers related to proof. Any of them, it corresponds to the proof to the Gödel number of the formula P, which is X. Or we don't have a proof of this correspondence. We should say. So proof PROV parentheses YX is something saying that the Gödel number Y is corresponding somehow to the Gödel number X. So Y is the Gödel number corresponding to the proof of the Gödel number of the formula with the number with the Gödel number X.
Right.
Mhm.
Right, and the fixed point would be this statement itself.
So I'm confused about that. I would think that the fixed point would be some specific value for X. But then
No,
here it's sort of saying the fixed point of this is this, and it has this free variable in it.
but there is a confusing there is a confusion about X as a free, because X, I believe that here X is a Gödel number, and the fixed point is an expression, and
Yeah,
it's not
that's what I think too, right? Because on the right-hand side, y and x are integers or natural numbers.
right.
It doesn't make sense to stick anything else as x in there, except for
Right.
integers. And so
Right.
the expression e of x, fixed point of this e of x, does it mean that the fixed point of the phi sub e?
Yep. But this is what I've been claiming. So yeah,
Okay.
the language is confusing. It's a fixed point corresponding to E, but it can't be a fixed point of E because E doesn't map things to things of the same kind.
Right.
Right.
That's why I was thinking maybe that he's missing maybe he should be encoding the right-hand side with a double, the angle quotes. Does it make sense?
Let me
Anyways.
back up just a little bit here on F, which he's saying takes a term with one free variable, another term with one free variable, to one with 0 free variable.
Right.
And then defines X here, but doesn't it still have a free variable on the right-hand side?
That was my initial question.
No,
X
it doesn't,
here
because
is now treated as a symbol that
Yeah,
it gets
sorry.
encoded. It's not a function of X. It's just a symbol that is being encoded now. It disappears.
But here
That's why
in
it's
theorem,
in 0.
right. But here we are not talking about Gödel encoding still, right? In this theorem. So Gödel encoding appears later on, and then X is something different. Or not because, or no, I'm wrong, because we have these up square, up brackets, right?
Yes.
Right. I know.
I did this in college. First encountered this, and it was still a puzzler there. But I mean, I think the key takeaway though is that we're living in a consistent and omega consistent theory, right?
What does omega consistent mean?
I think it means that you could have a sequence of sentences that get more and more complicated, like the limit of conjunctions, for example. So you could, instead of finite conjunctions, you could have an infinite conjunction or infinite disjunction. But the
Like for
terms
all or
are,
exist.
yes. Well, okay, I don't want to, I'm fuzzy on that one.
Okay,
So
sorry.
But
yeah,
right, but it is related with the kind of formulas that you are allowed to construct. I would say, for
yes.
right, for showing, for proving consistency, uh, it is so I don't remember it exactly, but I have here about something called induction on the complexity of formulas, and you define the true value of just a kind of simple formulas or atoms, right? And you define terms to construct from these atoms, from these simple formulas, through induction on the complexity of formulas. And you are allowed to, maybe to construct just not just finite formulas, something like that.
Yes.
So it is stronger. Omega consistency, I believe that it implies just consistent. It is. I will Google it, but I feel that it is a stronger condition.
Uh-huh.
Anyway, I feel confused about if X is a number or a free variable. I don't know. I feel that it is not well, expressed in the paper.
Right.
I mean, because when we get to, yeah, I'm still struggling with that because, right, we're defining G in terms of some formula, right? You give G some formula in the language and you then extract okay, some formula in the language.
Maybe taking a looking at another
Now
example
I'm
might help.
confused.
If you go to the next page, the Tarski's theorem, it's even simpler, right?
X is greater of a true theorem.
Right.
And then set E to be that.
The negation.
Right, of T. At X, though. Right. So X is free. But a fixed point of this would be
And
some
do they
value
actually-
for X.
Do they actually say a fixed point of E? Not just a fixed point of, so they're blurring the distinction between E and phi sub E right here.
Yeah.
Okay, so what's a fixed point of phi sub E? The proof constructs it as a closed formula C, such that phi E of C is equal to C, or is their equivalent.
Are we back at this one here? Is this where you're reading from?
Yes, in there. So just like ignoring like how we choose C, how we construct C. What does it mean for C to be a fixed point? This is the script capital C, right? So phi E is okay. So what does it mean to be a fixed point? So phi E of C is is E, is the formula E, which has one free variable, evaluated at the Gödel number of C. Okay,
Okay,
so if we
that's
take
what this
E,
is, right?
yes, but again, I'm trying to skip the definition. Sorry, the proof of it, and just say, what does it mean?
Oh,
If we go up a little farther,
okay.
just a little farther to the top of the page, what is phi sub E? It takes a formula, a closed
Where is
formula.
it? Okay.
No, yeah. Top of page 16. We're going a little faster.
Oh, you don't, okay.
So a
Oh,
little
why is my cursor not working? Okay, tell me when to stop.
That's good.
Okay,
We're defining phi sub E. We can feed it a closed formula, which here is referred to as P. And what it does is take the formula E, which has one free variable. It feeds the Gödel number of the closed formula P into that, thus getting a new closed formula. Yeah.
Right.
yeah,
Okay, so what's a fixed point? What does it mean to be a fixed point? It means that you have a closed formula such that when you feed its Gödel number into E, you get the same formula back in some sense. I think it might be an equivalent. Yeah.
you're saying
Okay.
that there's a fixed point of this is going to be some formula such that when you, yeah, such that when you feed it that formula, you get that formula out.
Yeah. So
Right.
E of the Gödel number of P is equal to P, or is equivalent to P.
It is consistent with the formula that we have below, right?
Meaning,
For the first application, right? We have a formula, and feeding two Gödel numbers, we get out a formula of out of this.
Right.
Right,
Remember that these
Right.
brackets aren't there, right? So basically this is a thing that takes formulas to formulas.
Right.
Well, here's the formula
Right.
that is the fixed point.
Right.
now
This
the
is the
question is,
formula.
for any specific E that we're interested in, what does that mean? So looking at the Gödel's incompleteness there, what would it mean to say that E of the Gödel number of
That
P is equal to P, is equivalent to P? It means that, so what is E of the Gödel number of P? It says that the statement P is not provable.
Right.
And that, because it's a fixed point, E of Gödel number of P has to be equivalent to P itself. The formula P, formula, sentence, same thing. So that's why they say it's a
so
sentence.
it's equal to basically the right-hand side. No, I don't know.
Yes. Yeah, that's also true. And in the application, Gödel's first incompleteness theorem, like for that choice of E, what does this mean? It means that if we say E of X for any particular X, it means that formula X is not provable. And the formula with Gödel number X is not provable.
Right. We have a Gödel number
Even though it's true.
for the formula saying that the another formula with the Gödel number X is not provable.
Yeah. So what happened, the fact that that this thing is a fixed point means that the unprovability of the fixed point, let's call it C, because that's what it is in the proof, unprovability of C is equivalent to C. It's the same as C.
So this formula is not right. This form through the coded numbers, this formula is saying that itself is not probable because they got right.
Yeah.
And the formula is the fixed point.
That means that the unprovability of C is equivalent to C. C, or more informally, C asserts its own unprovability.
Okay,
Right.
I'm fine with the Gödel first application at least.
Cool. And I think
with
that the Tarski version is somewhat simpler, but I think it will be. I think it also.
I have another question actually about this stuff, because I was thinking about imagine that we have this category about we have, for example, some Cartesian closed category, and we have this scheme, this diagram with the application phi with a fixed point. And we are interested about translating this diagram with this application into another Cartesian closed category. We want to transport this result, this application V sub E with fixed point for getting an incompleteness result, but in a different category, for example, something like that. Or we are interested about transporting the application without a fixed point, something like that. You know, transporting the property. How could we do that? I don't know. Which kind of property should have the functor that we construct? Does it make sense?
I'm sorry, I didn't get that.
Okay. So we have this kind of result, right? In a concrete Cartesian closed category, right? So imagine that we want to transport this diagram into a different category, right? For proving another result of incompleteness, but in a different category, something like that, in a different logic, something like that. I don't know, but
I guess
how
you're
could
asking if a functor preserves the incompleteness from
exactly
one Cartesian closed category to another.
right?
That raises a question in my mind. If I looked at this diagram here, the square, and I tried to interpret it in any Cartesian closed category, I would have to ask myself, what does it mean to have a fixed point? Does that even make sense? What is a fixed point of a morphism in an arbitrary category?
Mm.
I don't know. I don't. That may be part of what you're wrestling with, Antonio, or it may not. I'm not sure, but presumably, if we go back and we look at Lauvier's paper, we'll find out how he says that
Right.
categorically. I just don't know how it would be.
Because that would be a morphism, right? And you're asking something about almost the internal structure of the morphism.
Yeah. But I mean, certainly, if the commutative diagram should be preserved by a functor, right? That's a functor's job, basically, is to preserve a commutative diagram.
So I have understood that a fixed point may occur at some occasions, also in normal computation. For example, all which is divided if you take 0 and divide a bunch of numbers through 0, you always have the same result. Hello?
What are you saying? If you have a bunch of numbers and you divide them by 0, you get the same thing?
No, 0 divided by a bunch of numbers.
Hmm.
So that's a
Right.
kind of fixed point for me. So I understood it, because there's always 0. So it's a constant function somehow, or it's a bunch of
Yeah.
constant functions.
Hmm.
So it's not so special. It's just saying you got the same. You are stuck somehow, but the result will not change.
Wouldn't it be something more like multiplication by 1? Because you have
It's also
any
exa-
number, you multiply
exactly.
it by 1, you get the
Yes.
same number. So that's like
It's
a
also a
fixed
fixed point application, if you will.
But a constant function is not the same as a function with a fixed point.
No.
Right, because you put in 6 and you get out 0. That's not a fixed point.
Just as I understood it.
Hmm.
So inconsistency is not really, I think this use for inconsistency for fixed point, it's are different notions. It's not so happy.
Hmm. Before we leave, because we only have 10 minutes, I had a couple of questions from earlier. Where was this? This remark 1, basically, that there are sets that don't have a fixed point. And so it seems like an obvious contradiction to this theorem. But then he's saying that you really need to be talking about category and morphisms and things like that. But I was still unsure, like, where does this theorem like fall apart? I mean, you know what I'm getting at? It's like, it seems like he's saying this doesn't hold because there are sets with 2 or more elements that had fixed points or that don't have fixed points. So
Well,
No,
like
no, the opposite, right? The question is it possible to have a set or an object where every morphism from itself to itself has to have a fixed point? In set, that's clearly not true. And the example is this 2, right? But there are other structures where that may be the case, because you restrict the mappings, arrows, so that they all have to have a fixed point. And that's the kind of case where you deal within like lattices, lattice structures, which are a kind of generalization of open sets and functions between them. Then every continuous map, by definition, has a fixed point, even if it's the bottom element. So you can have a category where every morphism to itself has a fixed point, in which case the diagonalization does not apply, right?
okay.
Because you
Is that-
assume that, yeah, because you assume that there is a alpha without a fixed point. But if that's not the case, there is no alpha without a fixed point, then this does not apply. And that's why I claim.
Well,
if
if you're to take Y to be 2 and alpha to be not.
But that's the thing. instead of 2, you have true and false, but then you also have a bottom, which is less than true and less than false. And you have a definition of a function that's continuous from that domain to the same domain, then bottom has to always map to bottom. So then it's got a fixed point, which is bottom. The undefined is the fixed point. So that's one way of resolving this using a different kind of logic, different kind of set. Instead of 2, you check the complete lattice of 2 elements, which is T, F, and then a bottom. Actually, it's a semi-lattice, but
it
nevertheless.
seems like we get to choose these things, right? So let's say I chose Y to be just 2, not with a bottom. And that I chose alpha to be not.
Correct. If that's the case, then this theorem
is then saying that there's a fixed point of alpha, and there isn't. So
but that's
where
the
is
whole
this theorem going wrong?
The theorem
No,
doesn't
this
say
is
that there's a fixed point. The theorem says that we have representability. It says that
That's what I was wondering.
yeah.
no, it's
sorry,
proof by contradiction. We're saying that alpha is without a fixed point, and then the theorem, the proof is saying if there is a representable, if G is representable, then alpha must be have a fixed point, which contradicts the assumption that alpha does not. Therefore, G is not representable.
Actually, if we have on just the bottom, what we could what we could get from that, it is just a fixed point.
Right, but if alpha does, if you cannot find an alpha without a fixed, that is not without a fixed point, then the theorem does not hold, right? And that's my point, is that there are other categories like continuous lattices with continuous functions between them, where Cantor's theorem does not hold, where you have T, the domain of all continuous function, of objects, is isomorphic to the domain of all continuous functions from T into itself, for example. And that's how denotational semantics resolved the perceived contradiction in lambda calculus. And so Dana Scott came up with this model, not using set theory, but using continuous lattices and continuous functions between them that resolve that, the fact that in lambda calculus, X can be applied to itself. And in set theory, you cannot do that, because that leads to paradoxes, Russell's paradox, essentially. But in the continuous lattice domain, you can, because you're restricting your functions to be continuous functions. And that's related to computability, et cetera, et cetera. So
Actually, that's the point about this paper, is that, okay, so paradoxes actually don't arise if we restrict ourselves into the adequate domain somehow.
I'm sorry. I should probably go at the scheduled ending time. Y'all can continue, but before I do, could we schedule the next meeting?
Right.
Is the 12th of August good for everyone? That's 2 weeks from today.
So can you repeat it again? So
The 12th of August?
So half of August or 12?
Yes.
4th. Okay.
August 12th.
Yes,
12th.
2 weeks from today.
Okay. Right.
Okay.
It works for me.
Yep, works for me too.
Yeah.
Okay.
Right.
Well,
and what are we going to cover?
I think we will pop back to section 11.4, if I recall, of Science and Functional Programming.
Right.
11.4 or 11.5, somewhere around there.
Right. After this parentheses.
Yes.
Yeah. I think, just to conclude my thought about this, I think, Cantor and set theory has been an interesting development, but I think another related notion is intuitionistic logic or constructive logic, right? If you don't have the law of excluded middle for infinitary kind of reasoning, then you also don't have this kind of paradox either. If you stick with intuitionistic logic, then what you can prove are only constructible things, and then all functions that are constructible, you can enumerate them, et cetera, and therefore you cannot just have an arbitrary, assertion that there is a non-representable function. So, yeah.
So you're saying that in constructive logic, there's no
Right. You
no
cannot prove.
representable. There's no one of those F hats that basically enumerates
right.
all your.
That's right. You cannot have a unrepresentable function from y to, t to y. Yeah. So again, you're restricting the set of objects that you're considering, and so on. And that's why I think set theory, this is my little pet peeve, for finite things, for constructible things, it's great. But for infinitary things, once you get into that, like the continuum hypothesis, is independent, an axiom of choice, et cetera. Once you get into those kind of things, it becomes really not that useful, I don't think, about reality. But yeah. But it's good at showing. It's good at showing limitations of things. I agree. But
I have an example for this, but maybe I can show it next time or another time. Why set theory is not so great for number theory, for example.
Right. It doesn't really make its appearance in number theory. It's the problem is in measure theory and all those funny things that happen in measure theory because of sets. But if you don't stick to that, but if you stick to constructible reals and the constructible universe, then the world becomes, in some sense, more complicated because you have to prove things constructively, and that's sometimes harder. Like here, for example, you prove by contradiction. But supposing you could not prove it by contradiction, what do? Right? It may be not provable at all. So.
Oh.
So.
All right. Well, I guess on that note, we should probably wrap it up.
Yeah, this was an interesting excursion.
Yeah, I thought so too.
Right.
And maybe think a little bit more about the notation to make it clear.
Right. Just for finish just for concluding the discussion, just for ending this discussion, could I share my screen and show you what is the paper from which I was thinking about that? Because this one, I would like to share. Oh. Can you see my it is readable?
Yes.
Okay.
Yeah, but maybe
it is, but it's a little small.
Okay, I will increase the font size.
Yeah,
okay,
that's better.
Okay, so it was this paper about. Sorry, I will try to manage the camera, the window. So this one about undesirability and incompleteness in classical mechanics. So the point here is that something called Richardson functor is defined here. And we are translating or transporting the undesirability result from the language of piano arithmetic into the language of Zermelo-Fraenkel with choice, right? And we are constructing a functor. And I was thinking about this theorem from Lover, and I was thinking that we are constructing a functor translating this kind of diagram somehow, right? And translating the incompleteness from one place to another. I don't know if it makes sense to you, or if you agree with that. So L sub AR is the language of arithmetic, of piano arithmetic, with the axiom of piano arithmetic. And L of ZFC is the language of Zermelo-Fraenkel with choice. And I'm not sure about how it is done, but I feel that at the end of the day, here the whole thing is nothing more than translating the diagram with the incomplete, with the diagram into from one category to another. Right. And if we can find a way to translate this diagram through categories, we can get incompleteness result in different frameworks, in different, in different domains.
Different categories.
Like, right, we can get incompleteness result from arithmetic. We can construct maybe incompleteness results in analysis, or indecisibility result in EDP, in solving ADP, or solving partial derivative equation, right? So we can get incomplete result in analysis, or in maybe another domains. And that's what.
Wouldn't you run into the problem that, right, in your first domain, your first category, you're using extra structure? It's not just a plain category. It's, it's got all this extra structure, like
it's not just
products and exponentials and units and things like that. And you would, if you came up with a functor to another category, it would have to be one with all that same structure. And that might not be something that would work in these other settings. I don't know. That would be my fear, that it wouldn't carry over. Maybe
because because here something it should be embedded in the other thing, right? Actually, I was not able to find a rigor definition about what is the Richardson functor. It is something that takes things in from the Diophantine sets to reals, or to real functions. So something like that. But I have not clear in mind from which category to which category this Richardson's functor is constructed. But I was not able to it is a not a a recent paper. It is from 1991. So but do you feel that
But
it could be
mathematics
really
moves slower than computer science, so maybe it's okay.
right? Right, but because I found it quite something that so the Richardson functor, which as it provides a way of translating a statement about natural numbers into a statement about real numbers. That is, we get an equivalence between sentences which are formalized in arithmetic and sentences which are formalized in the theory of elementary function of a real variable. So we are embedding one theory in
That's
another.
nice. It's a great idea.
It's, I mean, I could see the embedding, but this is saying equivalence, which kind of would imply it goes back the other way, that you could take sentences in, you know, the real world and turn them back into sentences.
It is
And,
not it is not an equivalence. It is an embedding. It is true. That the thing is
but
that
on
the
line
point is
3
that,
there, it says we get an equivalence, but maybe it just means embedding. Is that what you're saying?
right.
But it's only in one direction. Otherwise, it's not going from the complicated into the simple. That's not possible.
Yeah. That's what I was saying.
But equivalence, it is not an equivalence between these two categories or in the categorical sense,
Okay.
I guess.
Okay.
But the point is that somehow we can, or this functor, transport the incompleteness result from arithmetic to the other category, from to the other category in on where the arithmetical category is embed and it is transporting incompleteness result. I guess that, or I would say that it is like constructing a kind of functor for this embedding. I don't know. But, you know, conserving the diagram that we saw before.
So that's no wonder. I think you could not prove in natural numbers. You can't prove in more complicated systems. In more complex number systems.
Right, but maybe something that is maybe something that's not provable just using natural numbers could be provable in the large system.
Right. It seems like if you have something that says that these formulas in natural numbers are not, you know, not provable or whatever, not complete, transport it over into the real numbers, the statement's only going to be about
It's like,
I don't think it's going to be a statement about all real numbers. And right.
I feel something like
I don't know
we have this diagram before in using just natural numbers, the arithmetic, right? And we have functions without fixed points, right? No, right. Not without fixed points, but we have functions with fixed points, right? It seems like we preserve some fixed points somehow because the incompleteness still is there where we translate from one category to another, applying the functor.
Thank you for the paper anyway. I think I will have a look at it.
Okay. This is the title.
Okay, I think I need to go.
Yeah,
So
this has been very interesting.
Yes,
So,
interesting.
yeah.
Indeed.
Yeah,
Thank you for recommending it.
yeah.
Yeah.
So thanks, Antonio. And I guess see you all next time, and we will get back to science of functional programming and taking a look at applicative functors, or actually it's contrafunctors that we had gotten to.